But yes, it is Q&A, so hit me. That's going to be a really short class. Yes, ma'am.
Did you end up like figuring out if that worked or not, the differential equation solver?
No, I didn't go to the website at another spot. What if we try a different browser? Okay. I switched from Chrome to Firefox. It worked perfectly. So you'll notice it gives me options for methods. When I click on options of methods, it gives me variation parameters, undetermined coefficients as options available once I type in the equation. Math24.pro. I don't know what it is. Chrome hates it. Or maybe the university hates it. I can't tell. Let's see. What was that ugly problem we did at the end of class yesterday? So we had y double prime plus 3y prime plus 2y equals 1 over parentheses 1 plus e to the x, close parentheses. And I wanted it to do it with variation of parameters. What do you mean an error has occurred? Why has an error occurred? Try again. All right, let's turn the variation of parameters idea off. Let's do it however you want. I guess their server is down, but normally it works. Let's just do 0. Do the homogeneous one. Standard ordinary differential equation. Y double prime plus y equals 0. I should get cosine and sine. It was working the last time I did this. I don't know what's going on with the website now. So jump to Wolfram Alpha. Solve y double prime plus 3y prime plus 2y equals 1 over parentheses. 1 plus e to the x. There. And there it walks through my solution. But unless you're going to pay for the pro version, you're not going to get the step-by-step on this one. The DE Solver Pro used to do that for free. And you'll notice they have the simplified version. Because we had that extra e to the x that we had to get absorbed. So that's why I said Wolfram gave me a different answer because they hadn't given me the solver worked out. Make sense? All right, maybe I'll have to take that website away because it isn't working like I wanted to, and that's not helpful to you. Yes, sir.
Can you just help me with 4.6, number 6? So when we do YC, can you just explain to me, what would C1 and C2 be?
Do we have initial conditions? Then we leave them as C1 and C2.
Yeah, it's Y double prime plus Y C2X.
Right, but I start with the equation y double prime plus y equals 0, right?
You plus the negative I.
So and when I do plus or minus I get C1 cosine x and C2 sine x, right?
Why is it cosine X?
Oh, okay. So really, it should be y equals e to the ix, right? And that's equal to cosine x plus I sine x. But here's the issue. Y1, Y2. That's cosine of minus x plus I sine minus x, right? If I add those, oh, wait a minute. Cosine of minus x, cosine is even, that's the same. Sine of minus x, sine is odd. So if I take y1 plus y2, I get 2 cosine x. So I might as well use cosine of x instead of y1. And if I do y1 minus y2, I get 2I sine x. Again, this can be part of my constant, can't it? So whenever I see complex numbers, it's easier just to use cosine and sine. I will add a video to our list. This channel, just this week, put up something we're going to deal with literally next week. This is a video about Laplace transforms, and that's chapter 6. We're doing that next week. But the video that is immediately before this, I need to look at the YouTube channel to show you the link, is right here that talks about why complex numbers and exponentials. That video goes through exactly what I just went through and shows why complex numbers are the pieces we're going to use to solve differential equations more often. Let me put a link to that. Share, copy link. Let's go put that on our Canvas page right now. Web links. Plus add external URL. That's the link. 3 blue, 1 brown on complex numbers as rotations. Bang. Publish it. Here we go. And we'll unpublish the Math 24 server and we'll figure out why it's up later. So the whole idea is that it's easier for me to work in cosine and sine than it is to work in complex exponentials, even though I like complex numbers and I'm a freak. More. Oh, Noah, if it's e to the something that's not just I, if it's e to the a plus bi, we write it as e to the a, e to the ib, and then we get e to the a cosine b plus I e to the a sine b. And so my pieces are C1 e to the a cosine b x and C2 e to the AX sine BX. But in the example we were just doing, A was 0. So e to the 0 is just 1. And that's why it's just 1 cosine X and 1 sine X up there. My favorite equation in almost all of math is that e to the I theta is cosine and sine. It's not quite the one I'm getting tattooed on my butt, but there you go. Yes,
I'm having trouble on 18 finding the particular solution.
in 6 or 4, 4.4. So in 18, I've got e to the 2x cosine x minus 3 sine x, right? What was our homogeneous solution?
Y double prime, C1 e to the x cosine x plus C2 e to the x sine x.
Well, crap, there's part of the problem because e to the 2x cosine x is sitting here, right? Oh, that's different because this is e to the 1x. Okay, so that's different enough. So I'm going to say that I believe that yp should be a e to the 2x cosine x plus b e to the 2x sine x. Because that'll be an a with a cosine and an a with the sine, but with the e to the 2x rather than an e to the 1x. Now, I think the problem is really going to come from doing the derivatives here.
Yeah, that's where I a lot.
Oh, yeah. Yeah, we're looking at product rule and gathering all the like terms over and over and over again.
Yeah.
So here, we'll just do the first one. The first derivative, yp prime, a 2e to the 2x cosine x plus the derivative cosine is minus sine, so change that to a minus a e to the 2x sine x plus, now I'm going to rewrite the order here, 2b e to the 2x sine x, because that's the derivative where I do the e. When I do the derivative sine, I get cosine. So I'm going to get plus b e to the 2x cosine x. And now if I gather these, I have 2a plus b e to the 2x cosine x plus 2b minus a e to the 2x sine x. And then when I go to the second derivative, there's only one of each with the product rule. And it's the numbers in front that are the ugly part.
So I would group the A and the B with E and the 2x.
Right, I went with this is the a to the 2x cosine parts. And these are the e to the 2x sine parts. So those coefficients went here. And those coefficients went here.
So when I do the product rule for the second derivative,
I'm going to get 4 terms again, right?
Yeah.
But the first 2 terms are going to have the 2a plus b in them. The second 2 terms are going to have the 2b minus a in them. One of them will have a 2, one of them won't.
Okay.
Then I'll have to multiply all the coefficients together to gather those up. It certainly is not pretty. Excuse me. And this is the downside to the undetermined coefficients method in general. We're going to do a lot of taking derivatives and a lot of algebra to get there from here, as opposed to in the variation of parameters where I got to do a lot of integrals and determinants. Which is easier depends on whether or not I can use the undetermined coefficients, because that depends on what kind of YP I've got in the first place. More stuff.
You do the integral of secant.
Sure. I am going to tell you, though, I'm going to cheat. This is actually an exercise done in the calc book that pisses everybody off. I'm going to multiply by 1. I think this is right. I hope this is right. So when I do this, I get the integral of secant x plus tangent x on the bottom. What do I get on top? Hey, wait a second. What?
Just
What's the derivative of tangent?
secant squared x.
What's the derivative of secant?
Secant.
Secant tangent. If I do u equals this thing, then this is its derivative. This is 1 over u du. What's the integral of 1 over u? Which means I get ln of secant x plus tangent x. Now I am 100% telling you that I have never in my entire life done this on the fly. I have this formula jammed into my head after teaching this course for 30 years. This goes on my formula sheet. So does the one for cosecant, which gives you ln of cosecant minus cotangent. Otherwise, I'd never remember this damn thing. But I was gonna say, I just did this the other week, so it happens to be fresh. I have no idea who came up with this, how they figured it out, but I love it. More questions?
Could you, the same thing that we did for number 6, could you do the same thing for number 12?
In
4.6.
4.6
I mean,
for number 12.
yeah. Take it to YC.
Okay, so what's the auxiliary equation? In 12, we have y double prime minus 4y prime plus 3y. I'm doing YC, it's set equal to 0. What's the auxiliary equation that goes with that?
R squared minus R plus 3, got R minus, R minus 1.
So that means that R is 3 and R is 1. So I get e to the 3x and e to the x.
I didn't. Thank you.
You're welcome.
See any other questions in the book, like 4.626, so I don't know if you could like make them up or. It's just like confusing with like. The polygons and multiplying by the x.
All right, but this is the variation of parameters one, right? Okay. So what did you get for the corresponding homogeneous equation? Let me write down the original problem. Y double prime, 4y prime, 4y equals 12x squared minus 6x e to the 2x. Are they both minus? No, this one's a plus. Okay. So your corresponding homogeneous equation is
C1 e to 2x, C2 x e to the 2x.
that e to the 2x and those matching e to the 2x's is what pisses me off, right?
No, it's not.
All right. So with that in mind, my problem is, what do I do about YP? If I were doing undetermined coefficients, I'd have to start adding more x's. But I'm not, I'm doing variation of parameter. So I need 3 2x2 determinants, right? W, y1, y2, e to the 2x, x, e to the 2x. What goes in the bottom lines?
3 to the 2x, and e to the 2x plus 2x e to the 2x.
So when I cross multiply, I get e to the 4x plus 2x e to the 4x minus 2x e to the 4x. So I just get e to the 4x. Great. W1 replaces the first column with a 0 on top and this disgusting thing on the bottom. right? 0 minus 12x cubed minus 6x squared e to the 4x. I multiply the x into that, and then the e to the 2x with the e to the 2x. Now, I'm not even going to do u2 yet, but u1 prime is w1 over w. So what happens when I divide that by that? You know how to integrate that. That's easy. W2, e to the 2x, 2e to the 2x is the first column, 0, and then all this garbage is the second column. What happens?
It's basically the same thing as before, you would just get 12x squared minus 6x, and then e to the 4x.
Perfect.
So when I get those equations for u1 and u2, the constants like should stay there in front of these.
Which constants?
Like you take integral of say like the 12x cubed, you would get 4x squared, or 3x to the 4, sorry. And that constant, the 3 just stays there.
Yeah. Oh, right. But now remember, what are we supposed to do with that?
Uh,
There you go. And then you'll take the u2 and you'll put it in front of the x e to the 2x, right? So you can have a bunch of stuff with x to the fourth and x to the third times e to the 2x. And then you're going to have a bunch of stuff with x to the third and x squared times x e to the 2x. Right? I bet a bunch of that stuff simplifies. A lot of very nice algebra happens here. A lot of things cancel, a lot of things simplify, a lot of gathering of like terms. Oh, and Mia, what happens at the very end when we're all done with all of that? Plug in y of whatever it is, y of 0 equals 1 and y prime of 0 equals 0. Solve for C1 and C2. But yes, those constants stay there. Yes,
On our homework. For the number 16, it says equals e to the t RTNT. Can I just rewrite it, put e to the x RTN x?
sure, if you want to use X instead of T, absolutely.
I'm not gonna lie, I don't know why it's not to do that.
Hey, variable can be whatever you want. I have no problem. If you just do, as long as you stay the same to the whole thing in X, good. There are a lot of problems where having a particular variable is an affect of what the setting is. So a lot of textbooks use T because they think of differential equations as things that happen in terms of time. Now, I'm thinking in time, well, then I want to do everything in T, and we think about what happens as time marches on. Our mixing problem, our population growth problems, they all sit in terms of T. There are problems that are multidimensional, we'll deal with, we haven't gotten to them yet, but I can deal with more than one variable. All of these are, y in terms of x. What happens if I have x and y and z and they all describe things, is y a function of x? Is z a function of x? Maybe x is a function of t, y is a function of t, z is a function of t. What does that mean? I could have two different populations or three different populations all going at the same time. We were talking about, what was it? Fish in the lake at one point, right? Or mice in the field. Well, if I have mice in the field, I probably also have predators that eat the mice, right? So I can think of the population of mice, and I can think of the population of the owls that eat the mice. And those will go together in different behaviors, but they'll both depend on time. Maybe I've got, another population as well in there that involves both of those. How do I deal with all three of them interacting with each other together? We'll get there later. But then there's a reason to not use X as a independent variable in situations like that. We tend to think of everything in T at that point. It's a holdover from physics. Which, if I really want to be pedantic, is really where all the related rates stuff comes from. And it's where all of the beginnings of calculus really started, because both Newton and Leibniz were working in physics, and they were working in motion two-dimensionally, and they did dx dt and dy dt separate from one another, and then figured out how to do dy dx after that. There's some really neat papers on that in the readings book that are referenced. Ask me more things.
in 4.438, it gave us an initial condition. Or I guess, it's a boundary value problem.
Right, technically, because they're not occurring at the same X. That counts as a boundary value rather than initial condition.
Okay, yeah, so. When I plugged them in. I couldn't find an exact solution for C2. So would there be a constant?
What do you mean when you say you can't find an exact value for C2?
Um. Like, so I solved and I got that C1 equals 0,
Okay,
but then when I did the second condition, I got 0 equals 0.
which means that's true for any value of C2. So I don't get an exact value, I get infinitely many values, right? C2 is a free variable. It's open. We don't just have one solution. Remember, that's the difference between initial value problems and boundary value problems. It is possible to have no solutions or infinitely many solutions or one solution in the case where I'm doing a boundary value. Initial values, it's either one or none. It's possible to have infinitely many in the case of a boundary value problem.
So would there be a constant?
Yeah, there'll be a C2 sitting there just staring at us. This works no matter what choice you pick for C2. I could pick 7, I could pick 32, I could pick negative pi over 6. Whatever. It works still. That 0 over 0 means it's true all the time, no matter what my choice is. Now, if we think about it for a second, let me push a little on this. My solution was something in trig functions, right? Exponential and trig.
Yep.
And our initial conditions was y of 0 equals 0 and y of pi equals pi. Yes? Well, yeah, the first one condition is great because when I plug in cosine, I'm going to get cosine of pi, cosine of 0 is 1, right? Now give me C1 equals 0 right away because sine of 0 is 0 and plus 0 when all the x's, because there were x's on the other side, those all go away. Makes my life easy. I determine C1 exactly. But then when I go to do C2, I get that sine of pi. Sine of pi is 0 again. Crap. This means that any oscillating function is going to go through both those points. Because if we think about this, this is a graph, right? You got some equation. And no matter what value you pick for C2, it's going to go through both those dots every time. And that means it could vibrate all over the place, but it's pinned down by those two spots. That's C2. That's also, by the way, why you call them boundary values, because they're like, here, I know these two edges. We'll worry about the rest later. It might even be worthwhile to graph a couple of those. Take a look at what they look like for different values of C. More questions.
I don't know if you're able to do this, but for number 16, there's one of the integral. If you help with that integration by parts. Or is it?
Oh, no. If that's the T inverse tangent, right? T arctan, X arctan X.
Yeah.
Okay. Yes, I believe that's integration by parts. In order, I choose for u the logarithmic. There are no logarithms. The inverse trig. Oh, I'm going to let u equal arctan x. And dv is x dx. That means that v is x squared over 2. What's du? What's the derivative of the inverse tangent?
1 plus x squared.
So uv minus the integral v du. All right, I'm going to put the 1/2 out front, and then I'm going to write x squared over 1 plus x squared. Cody, I'm going to do it again. See you sub. Well, not really. I can't quite do the u sub like I wanted to yesterday, because if I do u equals 1 plus x squared, then what's du? And I don't have a 2x, do I? I could do the at what? Right. So I'm going to do it like this, and I'm going to make it 1 plus x squared minus 1 on the top. And then that becomes 1 minus 1 over 1 plus x squared. And I know how to integrate this.
All right, thank you.
You're welcome. Calc 2. Lots and lots and lots of integral tricks. Kicks are for trades. Yep. Probably. Talk to me.
1 times x squared.
Just that? Don't what?
You made a fix.
Because you're going to be unhappy. Chapter 7, Section 3 in the calc book. This is a trig substitution. Instead of u equals something in x, I'm going to set x equal to sine theta. Why sine? Because I'm subtracting. When I subtract, it's either sine or secant. We'll start with sine. Okay, if I do that, what's 1 minus x squared become? Which is which means what happens to my square root? Yay! However, if this is x, what's dx? Which means this integral is now the integral of cosine squared theta d theta. And that's chapter 7, section 2, integrals of trigonometric functions. I hate dealing with cosine squared. It's disgusting. Out come my giant pile of trig identities. Trig identities. Double angle formula. There are 2 double angle formulas. There's one about sine of 2 theta, and there's one about cosine of 2 theta. This is why we get formula sheets. I'm remembering lots of things from a long time ago. Double angle formulas. The internet is your friend if you don't remember these. Look them up right now.
Sine x, cosine x. Then which one would it be?
There are multiple versions of the cosine one, right? But they all involve squares, don't they? Does any of them just involve cosine squared?
2 cosine squared x.
Let's rewrite this version right here to get the cosine squared all alone. This now becomes the integral of 1/2 1 plus cosine 2 theta d theta. And that I can do. What do you sub for the 2 theta? Now I want you to look at what we just did. I want you to look at something that's, kind of sitting here making me throw up a little in my mouth here. 1, 2, and I use 3 different integral tricks required to do this one integral. But you learned them all, Mia. You did in Calc 2. I have witnesses. You were there.
So you get the sine 2 theta in your answer, and you have to use the double angle formula again.
Yes, but I can go just one step further. I put that back in this. Right now, everything's in sine and cosine. But remember, we have this. right? X is sine theta. Sine is which two parts of my right triangle?
Opposite hypotenuse.
So what's this?
Or 1 minus.
Which was the same thing we started with in our integral, isn't it? That's why I know sine's the right one to use, because it's the same thing. And then I have sine of theta, and I have cosine of theta in terms of x. For the record, unless I'm grossly mistaken, this problem is actually one of the examples in the chapter in the calc book. Chapter 7, section 3. I like the other one in this problem better. There was an X on the outside of the other one. Ask me more things. honestly don't have a reason to keep your butts nailed to these chairs. Talk to me. Or we'll just say, I'll see you all tomorrow. Which is it? I was gonna say, somebody just raised their hand. Sorry, what's up?
I was gonna say, we did the same thing that I did number 20, just minus YC.
Okay, so what's the setup for number 20?
1y double prime minus 4y prime plus y equals e to the x over 2.
Oh, you said just find YC, right?
Yeah,
So let's ignore that part for a moment. I'm going to set it equals 0, right? So if I do that, then my 4r squared minus 4r plus 1, that's my auxiliary equation. What are the roots of that?
2r minus 1 squared.
Oh, so if it's 2r minus 1 squared, then I get r is a half, but it's twice, right?
Yeah.
So I get C1 e to the 1/2 x. And then what's the second part?
X e.
Perfect. You're welcome. Because that's what happens with a repeated root.
So I don't even look at really like what it equals to.
Not until I do the YP part.
YP is one.
Right. Particular solutions for the non-homogeneous corresponding homogeneous YC for the complementary part. I just set it equal to 0.
Thank you.
You're welcome. I wish you all a happiest rest of your day. I will see you all tomorrow.